Hey everyone, it's Professor Miller. I wanted to talk a little bit about naming some more. Some of you got bits and pieces of this in your lectures, but it's something that's kind of a sticky point for most of us, so I thought another quick video to remind you about some naming facts would be a helpful thing right about now. So I have new lecture notes for Chapter 2 that you can find in Module 4. Okay, so if you look in Module 4, you're going to see lecture notes. And I moved this from Chapter 1 so you could be reminded of what elements we need. So I said there's 45, and they're listed right here, atomic numbers 1 through 36, and then this selection, because these are commonly used. You got to recognize the name and the symbol. So this game lets you practice that. You can choose which items you want, and it just quizzes you. Okay, so another thing to quiz yourself on, and you can also make a Quizlet or flashcards or whatever you want to do. But the other thing to know about is the polyatomic ions. And so we talked about that you need to know the ones that end with just an ATE, like our friend chlorate that I used as an example in class. So you want to focus on those first, and then anything else that doesn't have a pattern. So ammonia, I'm just going to make stars on all the ones you got to start memorizing. Okay, so the purple stars are things that you need to memorize. Either they are the basis for other names or they're very common in and of themselves. The blue stars are things that are derived from purple stars. So for example, hydrogen carbonate comes from carbonate. It's just carbonate with a hydrogen put onto it. Hydrogen sulfate's the same way. Thiosulfate does occur, and you are going to use it in 142, but it's not a deal breaker if you don't immediately recognize that right now. It's a goal to work towards. And then we have the ITEs, the hypo-ITEs, the perchlorate, like the ATE. These ones. Okay, and so then we also spoke about, in most of our classes, we had a conversation about the series here where you have the same central atom, we call it, so the same thing in the beginning, and you're just changing the number of oxygen. So if you know what the ATE ending, what the formula is for that, you can derive all the rest of these. So if you add one oxygen, you're going to get a per prefix added and still have the ATE ending. The middle part is the root word. That changes depending on the element. So this is chlor because it's chlorine. Chlorate is the one I told you just got to know it. So you have to know that chlorate is ClO3 minus 1. If you go one less oxygen, you get the ITE ending. And if you go two less from your base, you're going to get hypo, which always means less than, and ITE. You'll notice again that all the charges are identical. They are also identical to the element when it is ionized. So chlorine is a -1 charge on the periodic table, and its polyatomic group, when you add oxygens, it's a -1 as well. That's true for most of them, not all of them. Phosphorus is a -3, sulfur is a -2. Nitrate doesn't follow the rules. Nitrate is normally a -3, so you just have to remember this charge. But some of them you can get off of the periodic table. And I also just want to point out, the only peroxide we're ever going to see is hydrogen peroxide, H2O2. That's the only testable name I'm going to give you. Otherwise, if you see oxygen, it's probably part of a polyatomic, or maybe it's attached to hydrogen, like in water. But peroxides specifically mean that the oxygens are attached to each other and each of them are attached to something else. This is a special molecule. It's very reactive. But the only one we're going to find in Gen Chem 1 is hydrogen peroxide. And then the other thing I wanted to point out here is chromate, CrO4 2-. This looks like it should be ionic, but we're going to learn in Chapter 7 why it isn't. Same thing for manganese over here in permanganate. These are covalent compounds in this entire list, including the ones that have metals, which is confusing because I just told you if you have a metal and a nonmetal, it's an ionic bond, but it's not always true. So these all act as covalent compounds, and the difference between chromate and dichromate This is the only place I'm going to ask you to use the phrase di for a metal, but the difference is that dichromate has 2 chromium on it. Okay, so just memorize these. That's task number 1 after you know the elements, okay? Then you can start putting them together with ionic compounds, like in these examples. So pause this really quickly, try these, and then come back to me and see if you get it right. All right, so this one here, Cu is copper. Copper has 2 options on the periodic table. It's either a +2 or the periodic table. So if you go to the link that I provided you in class, you'll find this version of the periodic table. If you actually download it and install Adobe Acrobat Reader, which is free, you can rotate it so you can see it properly, or just print it, landscape, and you'll have it then, right? So copper is Cu, and it has a +1 or a +2 charge. Okay, so that tells us that we have to have Roman numerals there in order to tell CuCl2 from CuCl. They are both compounds that exist, but they have completely different properties. So I'm just going to make a spot there for that. And then I know that chlorine always becomes chloride, so the ending always ends in IDE if it's a chlorine by itself. Now, I have 2 chlorines, and every time I have a chlorine, it's always a -1 charge when it's attached to a metal. So if I have 2 of those, then my anions add up to -2, and that means that my cation has to be a +2. So I'll put a Roman numeral 2. When you type this, we usually use the letters II to show that. All right, so next one. So this is a polyatomic group. The first chloride is not, but this one is. So the name just comes right off of the chart. And again, hopefully you're moving towards remembering those names. Eventually, you're not going to have it on your final. So work on that. Test yourself. Try to do names without the chart first, and then go back and check. The copper part is the same, and we also not only need to know the name, but we have to realize what the charge is. So sulfate is -2, which means that this copper also has to be a +2. Down here, it's going to end the same, but the first element is different. This is magnesium, and magnesium is always a +2, so I don't have to use Roman numerals here, but I could. It's not incorrect to also say magnesium 2 sulfate. Now you'll notice the Roman numerals are cozied up with the metal and they're in parentheses. That's kind of a requirement for naming it correctly, so make sure you're using the right punctuation. Another chance to practice. I'm going to pause the video and just put the answers up. You should pause the video and try it before you look at it. Okay, so I hope you got all these right. I think people will be confused by the first one because the charges are strange. Remember that phosphates are a -3, and iron cannot be a +3 here because we have subscripts. So we have to think about how those add up, and then basically they both become a 6+ and a 6- for the anion and the cation. People have a hard time saying KMNO4. The name for this is potassium permanganate. So you kind of say every syllable there. Don't skip them. So permanganate. The caption said permain government. That's not right. So use the spelling on the slideshow here. And then ammonium chloride, super common. You're going to see it all over the place. Okay, so the next classification of compounds is acid naming. And some classes we talked about this, but it seemed like we were still confused, so I wanted to go over it. In order to name polyatomic acids, so hydrogen in front, aqueous at the end, and then you have a polyatomic group in the middle. In order to do that, you have to know the name of the polyatomic group. So if we're still struggling with that, go back and memorize those first. Because you need to know the ending. If the ending of the polyatomic is ITE, then we're going to take that off and replace it with OUS acid. If the polyatomic group ends with ATE, then we're going to take that off and change it to IC acid, ic acid. So, for example, ClO4. So we remember from our discussion a few minutes ago that ClO3 minus 1 is chlorate. And we remember that when you add one more oxygen, like ClO4 minus 1, we call it a perchlorate. I'm running out of space. There's an E at the end. So that anion, that polyatomic, ends with ATE. So we go up here and we say, okay, well, I ate it, and it was icky. So that means the name of this is going to, the per stays, we're going to leave that, and the chlor stays, but we take away the ATE and we replace it with IC. And then we add acid, so that's perchloric acid. Super dangerous. I had to call the fire department once when I found a company that had it very near exploding, so don't play with it. Okay, so this one, an acid again because it has hydrogen in the front and AQ at the end. This one is from sulfate, so the same rule applies. We're going to take off ATE and add ic acid. This one's a little unique because we also add extra syllables. So instead of just saying like sulfate, sulfic acid, we actually add some of the original letters from the parent here. So we're actually going to call it sulfuric acid. Now, if you didn't remember to add these extra letters, I wouldn't mark you off in the beginning, but you should recognize that when I say sulfuric acid, that means H2SO4. It's a little bit of a deviation from our rules, but it's an important one. It's an acid that we see a lot. This one is nitrate, so this one becomes nitric acid. Okay, and then lastly, NO2, nitrate. So 8 is great. It has a higher number of oxygen, so 1 less than 8 is ite. So this polyatomic is nitrite. And we just said ite becomes us, so nitrous acid. And these two acids, nitric acid and nitrous acid, have really, really different properties. So that's why we have different names for them. Okay, so hopefully you're getting the hang of it. Pause the video, try these out. Okay, so these are the answers. I think people might be confused by a couple of things. I want to point out that hydro happens, like hydroiodic and hydrofluoric. Hydro happens when there is no oxygen in the acid, so not a polyatomic. We call these mineral acids usually. Hydrocyanic can be confusing because it doesn't follow any of the rules that we specified with ATE and ITE. So cyanide ends with IDE, not isocyanide, just cyanide ends with IDE, which isn't one of our ATE or ITE rules, but we still change it to ic acid. And the hydro comes from not having oxygen present. If it does not say AQ, or you don't have any evidence that it is dissolved in water, if you're doing this in lab, you would call it by the binary naming method, hydrogen, cyanide, and the name stays the same for the polyatomic. Acetic acid is super important. You produce it in your body. You eat it all the time in the form of vinegar. And also we use it in the lab very, very frequently. And there's two different ways to write this. So you can write it the way you do in Gen Chem, or when you get to organic chemistry, acetate gets written out like this, and the acidic hydrogen is put there. You'll learn about why that is if you take organic, but you need to recognize it both ways. And then, of course, going the other way from a name to a chemical formula is important. We had just done nitrous, so you probably got that. Hydrogen acetate is like acetic acid, but not dissolved in water, a pure substance. So it might be a liquid, a gas, or a solid. And of course, hydroiodic is an acid, and it's just made with iodine. Alrighty, so our last little bit of naming here is about hydrates, and this is important in a lot of ways, but in particular, it's going to come up with experiment 4. And so in experiment 4, you're going to do a whole bunch of series of different reactions. And part of your job for the at-home part of experiment 4 is to translate from names to formulas for 14 different reactions. And so that process requires you to understand naming, and it requires you to understand balancing reactions. So you should watch those videos prior to trying to do that. You're also, in the other part of that experiment, making alum. And alum is actually a classification of compounds, but the one we're making happens to have 12 waters attached to each piece of the salt. And that's actually really, really common. You've probably used a product you can purchase from almost anywhere with personal care stuff, like, you know, Band-Aids and any of those types of products. And that item is called Epsom salt when you buy it. But if you look at the label, almost all of the packages have the actual chemical name on it, which is kind of interesting. You don't see that a lot. And it's right. And it also sometimes has the formula. So this is the formula. And if you've never seen Epsom salt, it's fun to check out. It's good for soaking sore muscles. Magnesium helps with muscle problems like that. And a variety of other stuff. But if you buy some Epsom salt, you'll see the crystals are dry. They're sparkly white powder, essentially. And even though there's 7 waters stuck to every magnesium sulfate, it's still a dry powder. Okay? And so these waters are actually stuck on the molecular level, so we call it a hydrate. You could take them off. All you got to do is like bake it, and it'll heat that water off eventually. And you can actually measure a change in mass even, due to losing 7 waters for every magnesium sulfate piece. All right, so that's what a hydrate is. And they actually have completely different properties when they're hydrated and when they're not, like mass, for example. But also color can change. So this is an example. I think it's cobalt chloride. Actually, it's not cobalt 3. I'm wrong there. It's cobalt 2 chloride. So let me fix that. And as it turns out, the purple that's shown here in this photo is probably cobalt 2 dihydrate. And this kind of, I don't know what you want to call that, this more red color. Oh my goodness, that is not carbon monoxide. Hold on. Made my O too big. This is why punctuation matters, right? So uppercase, lowercase makes a big difference there. It's supposed to be cobalt, not carbon monoxide. All right, so cobalt chloride part stays the same, but over here, it's the hexahydrate version. So each cobalt chloride piece has 6 waters stuck to it. And if you heated it even more, it will actually completely drive off the water. By the way, to show heat, we sometimes draw a little triangle. It will drive off all the water, and this one is a very pale blue color, like a light blue color. Cobalt glass has that sort of same blue color, if you've ever seen that before. All right, so that's what a hydrate is. They have different properties, and some of them are colorful, some of them are not, like Epsom salt is white. But the hydrated version has different properties, different solubility, different everything, different melting point. Different color sometimes. And so here when we try to name this, what it will say for Epsom salt, it'll have the formula like so. And what you want to do is name the first part just the same as we always do. And then you add a Greek prefix to indicate how many waters. So 7 is hepta. And then you just add the word hydrate. Okay. And it's important when we get into the next chapter that you remember to add the weight of these 7 waters to the magnesium sulfate when you're calculating atomic mass. Okay. Oh, I put the name in the wrong spot, but you can put it in the right spot if you want to. This one over here is actually H2SO4 hydrated by 4 water each. So this has a picture on the molecular level. So here's 1 water. Here's another one. Here's another one. We got waters everywhere. So if you look at the guy in the middle, this one in the middle has 1, 2, 3, 4 waters. And these dotted lines show something called intermolecular forces. We get to that at the end of the semester. But it's just kind of showing how these are attracted to each other. All right, so here's your H2SO4 in the middle. That's where the other H's come from, by the way. So this is actually probably, some of these actually belong on the sulfate in the middle. And then you got the waters. So this whole thing repeats over and over and over to make the structure of the solid. And so if we were going to name this guy, it would be called dihydrogen. Again, this is actually considered a pure substance. It's not the acid because it's not AQ. If it were an acid and it was dissolved, we would name it sulfuric, but these hydrates would be gone. As soon as you put them in actual water, those hydrates go off on their own. And of course, tetra is 4, so we'll say tetrahydrate for this one. Okay, so that's naming pretty much all the compounds that I can think of. And so I made a different version than I showed some of you in lecture of this flowchart, because I've kind of think that the series of questions I ask myself has changed over the years. And I think maybe the first place to start is in figuring out whether it's covalent or ionic. And then from there, you ask yourself kind of a series of questions that lead you to the right name. And then I put red examples for you to have kind of an idea of the formatting and what it looks like. If you like this, let me know. If you don't, and you come up with a better way of thinking about how to navigate naming, please share it with everybody. I'm always happy to find new ways to think of things. I want you to understand that science is not one single answer. There's all kinds of different schemas, ways of thinking about things that you can use. So if you have a great one, please do share it with everybody.